lectures, just a bird's eye view. So the idea is that we wanted to study the S matrix because it was this very useful object that tells us about just time evolution in general. Whenever we have some process that takes a long time, where most of the interactions happen at some characteristic time scale, which is small enough compared to that long time, we can just think of about this like very long time evolution, and the operator that embodies that in field theory, it's this S matrix. Right, so typically in quantum field theory or effective field theory, we write the S matrix as 1, which is like trivial scattering plus IT, but we are interested in taking the classical limit. So I told you that maybe it's a good idea to write it instead of an exponential of some Hermitian operator, right? And that classically, there's an analog of this, which is kind of the canonical transformation that takes you from the initial phase space of the scattering process to the final phase space in the classical theory. Okay, and there's an object here, I, which kind of will be the generator of canonical transformations, which it's a thing that we want to learn how to extract from the S matrix. Okay, thing is that fortunately this S matrix is heavily constrained by fundamental principles. So I explained how these ideas let us construct things like the 3 graviton amplitude, 2 scalar 1 graviton, and kind of gravitational Compton amplitude. So these were just a few examples, but to give you the idea that we really know how to compute these things even in gravity. Okay, but now I want to go back and understand actually how to take this classical limit, and more generally, kind of in which regime in gravitational scattering we expect to recover classical dynamics. Okay, and it turns out that it's a non-trivial question. Okay, because so I will start by just reviewing something that many of you might know, but it will be kind of a warm-up because the kind of counting exercises that we will do will be very similar to what we will do later when taking the classical limit. So first, I'll just review GR as an EFT. Okay, and the idea being of understanding in different situations, what are the small perturbative parameters that we use when we do calculations in gravity? Okay, so when we think of GR as an effective field theory, what is the expansion parameter? What is the small parameter in this theory? Any ideas? Okay, that's certainly part of it, but this is dimensionful. So expansion parameters need to be dimensionless. That's right. In 4 dimensions will be G times the energy squared. So this is basically energy squared times m Planck squared. In D dimensions is D minus 2. So this will be D minus 2, D minus 2. Okay, so this is a small parameter when we think of GR as an EFT. Which means that actually this theory is a derivative expansion. It's not really, we don't have an actual small parameter in Lagrangian, we just need to count derivatives, okay? So typically when we think of GR as an EFT, okay, we think of, say, expansion around flat space, so we have the Minkowski metric and some perturbation, and there's gonna be many vertices. If you expand the Einstein-Hilbert action, in fact, there's going to be, in a generic gauge, there's going to be an infinite number of vertices, and each one of these vertices has 2 derivatives. Okay, all of them. So let's power count. Let's just count derivatives in some scattering process. So I will do, okay, one of the ones that we haven't done so far. So now for graviton, I won't actually construct the amplitude. I'm just going to draw some pictures, and we are going to count derivatives. And this is something that we're going to do over and over again. So in most of this class, there will be very few equal signs. There will be many wiggles because we're just going to count derivatives. Okay, but we need to get good at doing this. Okay, so let me look at the 4 graviton amplitude. So which kind of diagrams do we have? We have diagrams like this, and its permutations. We can have some contact term, also from Einstein-Hilbert. So let's power count this. Okay, so this one is very easy. This just has 2 derivatives in this vertex. So we expect that it will go as 2 powers of the energy. This one is a bit more complicated. It has two derivatives in each one of these vertex. So in the numerator, we have e to the 4. But in the denominator, we have e squared because we have one propagator. Okay? So we see that all of these terms actually will go like e squared, and there's a factor of g. So each vertex has a square root of g. So all of these terms will go like g e squared. So in principle, they're small. Okay. What about loops? So now let's add some loops. So let me add them up here. So let me draw, for instance, that I could have a box diagram, some triangle diagrams, a bubble, many permutations also. And let's power count this. So first of all, there's a simple rule, which is that each vertex has the same power counting as a propagator. So we can just collapse a bunch of vertices to count the simplest diagram. So the simplest diagram, for instance, is when I collapse these two propagators. So it will be something like this. Okay, so what will this look like? I will have a g squared, because I have one loop. I will have the measure of the loop integration. I have two vertices here, L squared from the vertices. And then I have two propagators, 1 and 2. Okay, so this will go like some energy to the 4th. So indeed, this will go like g squared squared, which is small, and in fact is smaller than this leading order. However, in practice, it's a bit more complicated than this. Because typically what happens is that you don't get just this power, but you get some UV divergence. Okay? So generically, you should expect that when you have this kind of loop diagram, this means that at some order in the energy expansion, there can be some logarithmic divergence. So typically, you would expect that this has actually a log of E over lambda. Okay, or 1 over epsilon if you're computing in numeric. And this tells us that we actually need to add some other operator to our theory. Okay, we need to add some extra term to Einstein-Hilbert, right? So GR as an EFT, the action initially you might have thought that is just this, but then you need to add more operators. So you'll need to add something that goes like lambda squared r squared plus 1 over lambda to the 4th r cubed plus dot dot dot. Okay, so at the same order, then we will find some counter term, which because it's an r squared insertion, it will have 4 derivatives, so it will have exactly the right power counting to cancel this. So this counter term will go like 4 derivatives, so it will go like essentially g squared e to the 4th also. Okay, so this is, okay, there's an accident in d equals 4, so this is just an aside. So in d equals 4, it turns out that there is no divergence at one loop, because the only r squared operator, which is non-trivial, is Gauss-Bonnet, which is a total derivative in 4 dimensions. So it turns out that there's an accident in 4D that there is no divergence at one loop, but if you go to 2 loops, then there will be an r cubed divergence that you can power count. So we see that we always have to add more and more operators. Okay, so this is, maybe you already know this. We can just compute order by order in this derivative expansion to fix accuracy. So as long as we are interested in predictions that fix accuracy, then we should be fine. But there's something funny here, because it seems that we need to know, like, okay, we could have in GR, this means that starting at order g squared, we need to know this information about these higher dimension operators. How come we can just solve kind of GR non-perturbatively? We have classical solutions, black holes, things like that, which are all orders in G. Okay? It must be that when we do classical physics, actually, this is not the right expansion parameter. Okay? So, and this is even stark if we actually think about the parametrics. Right? So for instance, when we think about the dynamics of the sun and the earth, so what is the typical energy of the sun in Planck units? So basically the mass of the sun in Planck units. I think this is something like 10 to the 38. Okay? So the small parameter for the sun would be 10 to the 38 squared. Okay? Because it would be E over m Planck squared. Okay? And that's not a small number. Okay? In fact, if you want some object whose its mass m Planck is order 1, I just looked it up this morning. I think there's like single cell organisms have around the right mass, like protozoum, like stuff like that. So these microscopic single cell organisms are the things that would already be strongly coupled in this sense. Okay. So, so why can we make predictions in GR at all if we have this large parameter? Okay. So this is even that is strongly coupled, okay? But we studied the dynamics of the moon and the earth, of the sun. So there has to be some other expansion parameter. So what is the, any guess what is the other small parameter than we have when we do classical physics? We'll get there, yeah. It's not that. That's a further perturbative parameter that allows us to do computations in the classical limit. But before we need to go to the classical limit, so there's another small number that appears. So any guess? It's a separation of scales in a sense, yeah. But which scales? No. No. Because we can study the dynamics of comparable mass stars or stuff like that. Something simpler, like, okay, what is the small parameter? When we take the classical limit, the small parameter is h bar, right? So what has units of h bar? Which quantity in angular momentum, exactly. So the actual small expansion parameter, kind of the classical limit, it's h bar over j being much smaller than 1, so large angular momentum, okay? How can you think about this? Just think, for instance, if you have some system and it's some quantum object, you have like the de Broglie wavelength divided by the separation, so the scales, the distances at which you're looking at this object. So this is something like h bar over the momentum, right? So this goes like h bar over PR, and the statement is that this is very small. Okay, so we want to understand this, how to take this classical limit, and kind of, it won't be this derivative expansion what we need to compute. We'll need to do something else. And in fact, we're going to see in a second that, well, we just saw with these examples, but generically we'll see that this is a large parameter. So we'll have to resum something, and this is related to the fact that I mentioned earlier that the classical thing is the face of the S matrix, right? Like we expect that in the semi-classical approximation, S will be I to the something over h bar, and that something can be large. Okay. So my goal, I'm going to think about, again, some 4-point scattering process, and think about the scales involved, and we'll try to draw a phase diagram of the different regimes that occur in gravitational scattering and try to identify what's classical, what's quantum. So once again, we have this kind of 4-point scattering, Now, they can be gravitons or anything else. Let's take them to be massless. So I have P1, P2, P3, P4. Okay, and I have the usual S, T, and U variables. So this will be the center of mass energy squared, T, which is P1 plus P4 squared, which I will call minus Q squared for later convenience. This will be kind of E squared times sine squared of the scattering angle. And then there's also U, which is minus S minus T. Okay, and I can consider either the amplitude in position space, which is as a function of S and T, which is this Q squared. But since I want to think about some classical process, it will be useful actually to think about this amplitude in impact parameter space. So I'm going to Fourier transform this variable Q kind of in the plane transverse to the motion. So let me define the following object as B. So I want to, so what is this Q? The statement is that this P3, P4 here, see, because P1 plus P4 is minus Q squared, then this has to be minus P1 plus Q. This has to be minus P2 minus Q to conserve momentum. So I want to do this Fourier transform, but I want to do it in a way that I preserve the on-shell conditions of these particles. So let me put in this delta functions, P1 dot Q plus Q squared. So this is just P4 squared minus M squared. So this is square minus M squared. In this case, M squared is 0, so just P4 squared. And also minus 2 P2 dot Q plus Q squared. E to the I B dot Q okay, and what is the picture here? The picture is that I have two objects that I'm scattering, and they will scatter with some impact parameter B and with some like fixed center of mass energy. Okay? And also a relevant scale will be kind of the quantum size of this object, which is the Compton or the de Broglie wavelength that I mentioned before. Okay, so what are the scales in the problem? So we have this, the de Broglie wavelength. We have the impact parameter. And what is the other length that we have in a gravitational theory? Yes, but that involves h bar. So which classical length scale do we have in? Yes, so you have the effective Schwarzschild radius that depends on the energy, which will be G times E. Okay, so the idea is that this classical limit, this means that this de Broglie wavelength needs to be the smallest length scale in the problem. R is like the impact parameter, it's just the separation between the objects. So I need to have a large hierarchy between these two. And of course, I want kind of the classical gravitational radius to be larger than this. So I have this, and here, if I want perturbation theory to be valid, so if the objects to be far away from each other, I should also have some hierarchy. This is not strictly necessary. For instance, when two black holes actually merge or collide and their horizons merge, that's precisely when the impact parameter is of the order of the Schwarzschild radius. Okay, but that's just strong coupling. So this is, so what are the two dimensionless quantities here? One is this divided by this. So H de Broglie divided by B, right? And this is something like, so B is the Fourier conjugate to Q, so it will be something like Q over E, okay? Or Q squared over S, okay? So the idea is that Q is going to be much smaller than S, and this is the classical limit. This corresponds to this limit of large angular momentum. And notice that that's also the small angle limit. Okay. Why is that? Because if we scatter things in gravity at fixed angle, then they're going to get very close to each other. They're going to probe very short distances, so we better make them scatter near the forward limit. Okay, so this being much smaller than 1, this controls classical versus quantum. Yeah, sorry. Yeah. Yeah. Let me just put a comma, meaning that I want this is the small parameter in practice in the amplitude. Yeah. But yeah, also this thing being much less than 1. Okay. And by the way, notice in particular, the fact that this hierarchy here is large is precisely what we said earlier. Because what is this hierarchy here? What is RS over de Broglie, or sorry, the other way around? No, yeah. This is 1 over g e squared. So this being very small means that this quantity is very large, okay? So classical objects have very large energy in Planck units, okay? Which is what invalidated our usual perturbative analysis in terms of derivative counting in classical GR. Okay, and then this here, and we'll focus on this later on, will be the other small parameter. So RS over B, this will just, being much smaller than 1, this will just be a weak field expansion. Right, so when we say that we have small g in classical GR, this is actually what we mean. Okay, we mean we are kind of at long distances or weak curvatures and stuff like that, but relative to some other classical length scale, not to Planck or anything like that. Okay, and in d dimensions, okay, the Schwarzschild radius in d dimensions, it's kind of the analog to this is d minus 3, so this is g e divided b to the d minus 3. Okay, any questions about this? So this is just scales, yes. The origin is that I want to integrate over these momenta while maintaining the unshell condition of these legs. So I'm going to fix the initial momenta. Right? There's going to be some kind of momentum transfer, but when I do the Fourier transform, I want to just do it over values of Q that maintain the fact that these two particles are on shell. So this delta function ensures that P4 squared equals 0, and this one that P3 squared equals 0. Well, the mass if they were massive, but here for simplicity, for now, eventually we'll make them massive when we have black holes and stuff like that. But for now, for simplicity, I'm making it massless. And notice that, in fact, because of this limit here, this means that Q over any of the external momenta, so these momenta are kind of MV, so they're of the order of the mass, or just proportional to the energy, which is smaller than Q. So we typically can ignore this Q squared here. So this just tells you that you're doing essentially the Fourier transform in the transverse plane to the kind of two initial momenta. Yes, even though they have large. Sorry, yeah. So Nico was asking some clarifying question of whether, that this answers the question of why GR works, even though like we keep perturbative corrections and stuff like that. So, so the first expansion, G squared small, was for particles. So it's a low energy expansion. But then this is, you can still have like strong fields. So particles that have large energy compared to Planck, but you can do some sort of perturbation theory and understand classical physics. Yeah. Okay, so I'm going to draw like a phase diagram of classical scattering. So this goes back to the late 80s, early 90s, the work mostly of Amati, Cefaloni, and Veneziano. So we'll locate what the classical part of the phase diagram is. Okay, so the axis here will be log of the impact parameter and log of the energy. So it's a log-log plot. Okay, so if we have kind of very large impact parameters, but we have small energies, so at very, very small energies, when G squared is small, okay, then we have here so-called Born regime, where kind of this tree-level approximation is okay. Okay, so this is when G is squared is much smaller than 1. But then also we want B to be large, because otherwise Q, so Q being small, because otherwise Q being very large would also be some issue. So there's going to be some boundary here that I'll try to explain now, which is when this slope is 1 over D minus 4. Okay, so here there's a question mark. There's these short distances. Okay, we always have problems at short distances. Okay, so this is where there will be some quantum stuff happening, and this is kind of not under control. Even at low energies, this is low energies on this channel, but in the other channel, this would be high energies. Okay, then there will be some other regime here where we actually have the dynamics, where some classical GR happens, where we actually have the dynamics of bodies and stuff like that, like of stars. And in perturbation theory, this will happen when this tree-level amplitude becomes large. So actually, this will be dominated, and this is one of the goals of today and tomorrow, dominated by diagrams like this. So things like, I will have to resum and exponentiate some class of diagrams, because kind of my phase will be large. So I need to essentially compute the logarithm of the amplitude, and there will be kind of, you can think classically, it's not a single graviton exchange, but if you have the dynamics of some system, they're exchanging many, many, many gravitons, okay, as time passes along. So we need to understand diagrammatically how that comes about. Then at some point, at this weird slope, 3D minus 10, there's actually gravitational wave emission. So I actually have processes where now I can emit gravitational waves. And I won't have much time to say something about that, but now I will explain where these powers come from. So we're going to do a very simple power counting argument that will teach us that it will be around here where we would expect gravitational waves. And then there's 1 over D minus 3. So notice what I wrote here is G over B to the D minus 3 when this is large. This is precisely this collapse regime where the two black holes or like two particles become within the Schwarzschild radius of each other, and then they will form a black hole. So this is called kind of collapse. And also a very important feature is that in this region here, the scattering is almost elastic. So the S matrix is basically like the absolute value is 1. So we know exactly what happens because we are recoupling. The particles just bounce off each other. The same is true here. Okay, here the absolute value of the S matrix will still be essentially 1. once I start emitting gravitational waves, whoops. Once I start emitting gravitational waves, there's other possibilities for the final state. So here, S will be approximately 1, because the emission of gravitational waves is a process which is suppressed in perturbation theory, in this R over B perturbation theory, but will be still sizable. But in this collapse regime, this S matrix will be 0. But by the S matrix, I mean this 2 to 2 S matrix in all of these comments. Okay. So let's try to understand these powers. Any questions about this? It's 0, the S matrix, meaning the probability of two particles just scattering away. Because essentially here, with probability 1, you're going to form a black hole. So if you're looking at this 2 to 2 S matrix, then essentially there's 0 probability that the particles will bounce off each other instead of forming a black hole. Okay, so yeah, maybe I should, here S means this. So 2 to 2.
I have a question. In the denominator, you have in the first line D minus 4, but we live in 4 dimensions.
Yeah, we'll see.
And also D minus 3.
Yeah, we'll see. This D minus 3 here is not an issue because, again, there's no real, so we were discussing in the other lectures, there are no propagating degrees of freedom, so actually this picture only holds for D greater than 3. This means that there is a logarithmic divergence. We'll see it now. Essentially, it's the usual infrared divergence from long-range forces in 4 dimensions. So in 4 dimensions, actually, in D equals 4, this 1 over D minus 4 actually means that you have a further logarithm of B, right? So the statement is that you will have that kind of E times log B is of order 1. Sorry, just E times log B. Okay. So let's try to understand these powers. And then we'll try to understand this exponentiation. So I won't do this calculation for you, but in the problem set, I asked you to compute the amplitude essentially for graviton exchange by 2 particles. Well, I asked for massive, but it's basically the same, or very close for massless. So the answer to this is something like 8 pi g. Okay, now I'm going to put masses just for the sake of it. So this will be P1 has mass M1, P2 mass M2. Okay, and the answer is 8 pi g, P1 dot P2 squared minus M1 squared M2 squared over D minus 2 divided by minus Q squared. Okay, so if you haven't done the exercise, please do it. So this is my S. Okay, no, also as part of the problem set, I'll ask you to Fourier transform this using this transverse Fourier transform. So let me just give you the answer. So if I do the Fourier transform, so A S B, you'll find that the answer is something like this. So it will be these factors here. So it will be 4 M1 squared, sorry, M2. Let me write it in 4 dimensions. Well, I guess I'll write it in D dimensions. But there will be kind of gamma squared minus 1. So gamma is the relative Lorentz factor. So it will be P1 dot P2 over M1, M2. And here I'm going to have essentially 8 pi g. Okay, from this I can just pull out factors of m1, m2. So this is just also going to give me m1 squared, m2 squared. And I will have gamma squared minus 1 over d minus 2. And there will be a b to the d minus 4. So this b to the d minus 4 is just the Fourier transform of this pole, which of course will be logarithmically divergent in 4 dimensions. Okay, so you already see the first boundary here. This thing here is essentially when this becomes large, right? Because this is just a tree-level approximation to this process. But I told you that for a classical process, at some point, this will become large. So this thing here goes like the energy squared, essentially. And here I have a b to the d minus 4. Okay, so this process, this object here, essentially like g e1, e2, or b to the d minus 4. So you see that it becomes large once you hit this boundary here, when you crank up the energy so that it's comparable to 1 over b to the d minus 4. D equals 4, there's a logarithmic divergence. Actually, I forgot. There's a, you can see it here. There's a gamma d minus 4 over 2. So this will be a gamma of minus epsilon, which will give you a 1 over epsilon pole, which will just give you a logarithmic divergence. Okay, so the idea is that we'll have to exponentiate this because there's going to be contributions that are comparable to this. So later on, we will actually power count all of these diagrams. So for instance, this box or this double box, and we'll see that these things actually just go like powers of this to leading order in the classical limit. So you will have it at tree level, and then you'll have the rescattering, and 3 times and 4 times, so we'll have to resum this in some way. So from this, we expect that this amplitude will be something like this. So it should exponentiate and then have kind of some quantum corrections, which we will study in detail. Okay. So this is this boundary over here. Okay. Now we want to understand when these gravitational waves become important. So okay, and the idea is that there should be a correction to this, because this is purely elastic, right? The absolute value of this, okay, this actually, to be more precise, this is IA equals this minus 1 plus quantum corrections, because it's the S matrix, so 1 plus IT, which exponentiates, so I need to subtract this part here. Okay. But at some point, there should be a correction. This is purely elastic. If I take the absolute value of this, I will just get 1. So there should be a correction, and the guess is that the correction will go like, I have this classical phase, and it should be something like exponential of the imaginary part of some process, right? So if this has an imaginary part, it will be something that decays, and this should be like the probability of emitting this gravitational wave. So this should go essentially like the cross-section for this emission of some extra gravitational wave, roughly. Okay, so when this becomes large or kind of close to 1, then, or close to this, is when we should expect that this process enters. So let's just look at the simplest diagram that looks like this, and as an example of just power counting. So let's look at this H diagram, so-called H diagram. So I will have these legs being on shell, but at the end of the day, an on-shell delta function is roughly kind of 1 over p squared minus I epsilon, p squared plus I epsilon. So in terms of power counting, it's just like a propagator. So let me forget that these are actually cut. Okay, so what will be the power counting here? So I'll have g cubed. I will have some powers of the energy. So each one of these vertices, where it couples to these massive particles, will give me a power of the energy. So this will give me E1 to the 4, E2 to the 4, because I have 4 such vertices. Okay, then I will have, okay, let's look at the propagators, right? So the propagators here, so let me look at this propagator. So this propagator will be something like, if this is P1, and this is L. So L is a graviton momenta, so it should be small, because it's like a Q, that's a momentum transfer. So this will be something like P1 plus Q squared minus M squared, which goes like 1 over 2 P1 dot Q plus Q squared, but Q is much smaller than P, so to leading order, this should go like P1 dot Q. Okay, so this is this kind of math propagators.
You have to integrate over it. I was asking.
I'm not neglecting it. Sorry, let me call this L. Okay, this will go like L, and later I'll introduce something called the method of regions, where we actually want to do this calculation more precisely, where we split the integration in kind of different regions, and then we see that different contributions will have different sizes. So for instance, if you have a contribution where L is very large, much kind of the order of these particles, then typically that will mean that you can expand this even further, and it will be some local counter term or something like that. So there will be some hard and some soft region, something like that. But right now, I just want to do a very naive counting of powers of energy and powers of Q, okay? So the idea is that L will be order Q because they're just these graviton exchanges which have to have small momenta in this classical limit where kind of the momentum exchange was much smaller than the energy. Okay, so that means that each one of these two propagators is going to give me a 1 over P and 1 over L, so an inverse powers of the power of the energy. So this will give me E1 and E2 because I have 1 on one side, 1 on the other. And then let's count derivatives. So I will have D4L. I'm going to have 1, 2, 3, 4, 5 graviton momenta. So I have L squared to the 5. I have 2 vertices with only gravitons. So this is an L to the 4th. And then these 2 inverse propagators give me a 1 over L each. Sorry, this is a D. And I told you that all of these are of order Q. So if you count this, this will go like G cubed, E1 cubed, E2 cubed, times Q to the 2D minus 4. And if you just do the Fourier transform of this is going to give you G cubed, E1 squared, E2 squared over B to the 3D minus 10. Okay, just by dimensional analysis. Because you're integrating over kind of D minus 2 components of Q. Okay, so when this becomes of order 1, then this sort of process becomes important. And this is this boundary here. Okay, and the last boundary is the easiest to understand because we said it's just when B becomes of order of the Schwarzschild radius, and then we just have collapse. So there's nothing to power count because anyway, this whole series becomes, each term becomes as large as the previous one. So. Oh, sorry. Yes, sorry. So there's 2D. Yeah, sorry about that. Because I have 2 loops. That's why I have 2D here, yeah. Yeah, so the last one is just a complete breakdown of perturbation theory. which we cannot calculate. And actually, one of the goals of these papers by Amati, Chaflin, and Veneziano was trying to get a peek into this region by looking at various terms in perturbation theory, but one has to stop here, essentially. Okay, any questions? Yeah.
Since we are considering arbitrary dimensions, if I have a string, perturbative string, and what regime will be there?
So, okay, let me make a side comment. If you look at those papers by these people, there's an intermediate regime where tidal effects come in. Because here, I was really thinking about point particles. But if you have some object that has some extent, then there's an additional scale, which is just the size of the object. Right? And typically, if you want your object to be something which is not a black hole, that means that in addition to this kind of de Broglie wavelength, we had like RS. Then we're going to have another scale, R, which is just the size of the object itself, which will still smaller than the separation between the particles. Okay, so there's some intermediate boundary here that depends actually whether it's above or below this line, in which dimension you are. So I don't remember from the top of my head the power, but let's see. Yeah, I don't remember. But there's some other boundary here that is where tidal effects enter, where you start to see the internal structure of the object. Essentially because at high enough energies, so you can imagine that the characteristic energy scale of the excitations of the object is going to be the inverse of this length scale, right? So so this will enter at some point. Where it enters depends on which dimension you are, but you can also kind of power count it. So let me make a comment about this, because I think now it's a good side. So this people call tides, tidal effects. And the idea is that we can take, okay, so we take like some planet or a black hole. We're just replacing by a point particle, like a cat also. Right? To first order, we just replace this by a point particle. And the question is, when do I need to include some correction to this? Okay, so if I say I represent this by a word line, so I can do either kind of point particles, a word line, or maybe some like scalar field. Coupled to gravity, well, there's going to be corrections to this. So for instance, here I could add a coupling that looks like integral of r squared along the word line. Right, or here I could add a coupling, which is something like the derivative of the scalar squared times r squared. Okay, and there will be some coefficient here. And this coefficient here will be suppressed by precisely this length scale. For instance, in 4 dimensions, this leading coupling lambda, this will go something like mass times the size of the object to the 4th. Okay, so you can find where this boundary is by essentially studying when do these operators actually activate in your perturbative expansion. Okay, when do these tidal effects enter? And it actually is highly dependent on the dimension. By the way, this is also somewhere hidden in the problems that I put. So try to understand why this is the correct power. Okay, any other questions? How much time do I have? Until 1. Oh, okay, good. Okay, so now let's try to actually understand this exponentiation. Right? So I want to understand how to go from usual perturbation theory, which is this realm here, to cross this boundary and really understand this classical regime where I have dynamics of objects that are interacting over and over again. So remember, I have these three scales that I wrote. Essentially, I have two parameters. One is Q over the energy, or Q over M, which this is classical versus quantum. And then I also have the other one, GMQ over just GMQ, which is the same as kind of RS over B, which is much smaller than 1. And this is just classical perturbation theory, or weak field expansion. So this is when we do perturbation theory in classical GR, this will be our expansion parameter. Okay, and as I mentioned, the intuition is that the S matrix, so kind of 1 plus IA, will be like exponential of this I with quantum corrections. But notice that it's not completely trivial to calculate. This is what we are after. This is the true classical object. This is eventually what will be our generator kind of the classical S matrix, so the transformation between the initial and the final state. And but for instance, there's an issue, we'll see, that there's an 1 over h bar here. So that means that when we actually look at the amplitude in perturbation theory, we'll find things which have many orders of 1 over h bar that we need to sort of exponentiate. And another issue is that there can be overlap of 1 over h bar with this quantum correction. So we need a way to kind of disentangle which pieces of the amplitude are actually classical. This thing itself, this classical object, this will have an expansion in GMQ. So it will start as something like GM1, M2. So there will be this log B or B to the d minus 4. I guess it's just Q squared momentum space. But then it will have corrections GMQ. And notice because there's more powers of G means that these will be hidden inside of loops. I wrote these ladders, for instance. So the classical limit will involve actually thinking about loops in this theory. Okay? So this is one of the key points, which classical doesn't mean throw away the loops. Classical means this. Classical means look at the face of the amplitude and expand that. But the nonlinearities will be hidden inside of this amplitude inside of the loops. Okay, so we want to understand how to do this expansion. So notice that both of these things is a small q expansion. So this is q over m, or q times gm. So we need to understand how to systematically expand the amplitude in this small momentum transfer limit. Yes? I think it's off, yeah.
It's working? Okay. Before the work of these peoples, of these physicists, was there any previous result about finding this action, this classical action?
Well, the leading order has been known for a long time. So when you look at the leading exponentiation, which is what we will discuss, this is sometimes also called the iconal phase or iconal exponentiation. So for instance, they call this regime the iconal regime. Turns out that there's various versions of this iconal when you go beyond leading order. So I don't really want to use that language, but yeah. So this goes back actually to Glauber and to like 50s, 40s, like when people just thought about like WKB approximation, semi-classical limits. It's an old subject in a sense. So basically, it's the same. In non-relativistic quantum mechanics is what we do when we write also the wave function as a phase times some absolute value, and then we just find kind of the classical equations of motion as some differential equation in the phase, et cetera, et cetera. So it's literally the kind of old-fashioned semi-classical approximation, and I'll comment more on that later, but yeah.
So it was expected to recover the Newton force, I mean.
Yes, I won't do this, but it's one of the problems in the problem set. So if you're interested, you can look at problem 3, where you're asked to do some of these Fourier transforms, and actually just the Fourier, I raised this tree-level diagram, but inside of that tree-level diagram, both Newton's potential and all of its relativistic corrections velocity are encoded. And then now we will draw some loop diagrams where you have, say, like these corrections at high orders in G from general relativity. Yeah.
Okay. Thank you.
Okay, so we want to look at this kind of small q expansion of the amplitude, sometimes called a soft expansion or just a classical expansion. And the idea is that all the graviton momenta are going to be of order q. So because we have this particle, so this is my massive particle or my very energetic particle whose energy is greater than m Planck. And then this is going to be hit by a bunch of gravitons, which all have momentum of order q. So it can build up because of many rescatterings to some kind of macroscopic amount, but individually, each one of these is very small. Okay, so that means that if this leg is on shell, these legs here, even though there are some virtual particle, this is almost on shell. Okay, which is precisely what I was trying to say here. So you see, if L is very small, this becomes singular in the limit where L is very small. So these propagators here, which would be something like P on shell plus L squared minus M squared, these are going to go as 1 over 2P dot L plus corrections that come from expanding this Q squared. So corrections that go like L squared over 2P dot M. Notice that this correction is order Q over M. So it's precisely the kind of corrections that I was saying that will be encoding this classical expansion. So I'm going to power count some diagram just by example. So we'll have that the external legs, they have momentum of order M, and kind of all the loops and Q. So these is much smaller than M. So we just want to expand diagrams in this limit. Okay, let me go there. No. So this is the example. I'm going to draw this triangle diagram first. Then we'll do the box. So this, first of all, is going to be order G squared. Okay. And then just by this power counting rule, so let's just count how this will go. So I have 2 graviton propagators. So let's do it in 4 dimensions. I have 1 loop momentum. I have 2 graviton propagators. So notice that we are playing this game of power counting over and over again. Actually, this is L minus Q squared. So let me write precisely what this is. So this will be L, be Q minus L, P1, P2. Then I just have this other propagator here. So this will be expanded in this limit. It will just be 2P2 dot L. In fact, let me first not expand in this limit. Let me first just write the whole thing. So this would be L plus P2 minus M2 squared. It's because I want to illustrate that actually we can be careful about this loop momentum and expand in various limits. Okay. So what's the basic idea? So now I'm going to explain something called the method of regions. Okay. The main idea is that if I want to compute this integral, and I have some parameters, so I want to compute the expansion of this integral in the limit where q is much smaller than p. Okay, but I have a loop momentum here that I need to integrate over. So in principle, there could be regions of the integration where L is much bigger than Q, or if it's of order P2, and kind of a region which is the one that we're interested in, where L is much smaller, so it's of order Q. Okay, so in principle, we would need to consider the various regions and try to understand which kind of contributions we get. So in particular, there will be two regions. There's the soft region, which is when L is of order Q, so it's much smaller than P, and there will be a hard region, which is when L is of order P. So let's first naively just expand in one of these limits. Okay? Let's look at the hard region first. So let me just look at the contribution from the part of the integration that would come from just expanding this when L is much larger than Q. Okay, so what does this look like? This is very simple. Because there's only one propagator which is not homogeneous. Because the propagator of the massive particle, if I say that L is of order P, that means that this is of the same size as this, it's of the same size as this, so I don't have to expand this. Here, L squared is also homogeneous, but now this propagator I will expand. So in the hard region, oops. I have that 1 over L minus Q squared will go like 1 over L squared, and then corrections that go like just Q over L. However, notice something. This means that whatever integral I do now will not know that the Q now just appears in the numerator here. Okay? Which means that the integral over loop momenta now will give me something which is analytic in Q. So this means that the integrals that I will have, they will be of the form ddL, and then just things that look like 1 over L squared with corrections that go like Q over L, but this is analytic. So what does analytic in Q mean in position space when I do the Fourier transform? If I have a polynomial in Q, what does this turn on in position space, in impact parameter space? Yes, right? So this means that these will be kind of derivatives of delta functions exactly at 0 impact parameter. So clearly I'm not interested in this region. Okay? So whatever contribution the integral gives, when this loop momentum is kind of too large, it's not going to contribute to what I'm interested in, which is this scattering at long distances. So I might as well just throw it out. It's part of the amplitude, but I don't care. I'm just not going to compute it. Okay. Now let's look at the soft region. So the soft region is precisely when this expansion happens. And this will be nice because now in the soft region, the integral will be very nice because I just have L squared L minus Q squared, and then 1 over 2 P2 dot L plus corrections. And now this is homogeneous in the mass or in the energy of this particle. Okay? So just by dimensional analysis, this integral, it will be some number, which I could compute, but I can just tell that it will only depend on trivially on Q. Okay, so this integral should go like 1 over the mass of the particle, m2, and then let's count. I have Q to the D, and then I have 1, 2, 3, 4, 5, D minus 5. Okay, so in 4 dimensions, this will go like 1 over m times absolute value of Q in D equals 4. So this is the soft. Okay, but maybe you tell me, there's something funny here. You did something which is not allowed. Like you just expanded this propagator, but then you integrated over all of the loop momenta, right? I didn't divide the integration domain into 2 pieces. I mean, technically I should have put some cutoff that separates the large momenta, the low momenta. I should have just computed one piece, the other, added them up, see the cutoff cancel. Okay. But this is where the magic of this method comes in. So let's just look now at the contribution to this integral from when L is large. Okay, I already expanded this momentum, but now let me look at what is the contribution when L is large, which means that now I can further expand this in the region where L is large. Okay, to see what is the part that I'm overcounting when I do the integral. Okay, so this is the overlap. So what is the overlap? So once again, now this propagator is homogeneous. This is the only one that I will be able to expand. If now L is much larger than Q, let me expand it. So this will go like DDL, 1 over L squared, and L squared, 1 over 2 P dot L, and then corrections that go like Q over L. But if I'm using dimensional regularization, all of these integrals are identically 0 because they're scaleless, right? I have an integram which is completely homogeneous now in the loop momenta, right? So this should be the integral of some dimension full scale, but the integrals don't depend on any dimension full scale. Okay, there's this P, but this is homogeneous in P, right? So this is identically 0 in dimreg because it's scaleless. Yes. This is the so-called overlap, because first I expanded the soft limit. I did the integral over all of loop momenta of the expanded integrand. And then I became worried because I said, okay, maybe I'm overcounting because even though I expanded the integral where L is small compared to P, I'm integrating over the region where L is large. So let me just re-expand in that region to see what is the extra piece that I'm getting. And then I find that it's actually 0. Okay? This is not always the case. Sometimes there is an overlap between regions, but it's often the case that there isn't. So if you're using dimensional regularization, because of this special feature of this regulator, which sets scaleless integrals to 0, then you can just expand away your integrand and then just do the integral as in the textbook, integrating over all of the loop momenta to extract the piece that you're interested in. Okay? Okay, so now using this result in the soft region, we are kind of ready to just count the contribution from this diagram precisely. So let me do the counting more precisely now, where I also include powers of the mass. Right, so this will go like G squared. I will have 2 powers of the mass from this vertex. So this was P1, P2, right? So I have m1 squared, m2 squared, actually to the fourth, because I have two vertices attaching to this leg. Then I have one inverse propagator that gives me an inverse power of m2. And in 4 dimensions, the integral just gives me q squared. So this, sorry, just absolute value of q. So this just gives me a g squared m1 squared m2 cubed over absolute value of q. And this precisely is a correction of the ones that I promised, because the tree level, we saw that it was gm1 squared m2 squared over q squared. And now this is a correction that goes like g m2 times absolute value of q. So this is small. Okay. So this is a classical correction to the scattering. What would happen if I further expanded this propagator? So we just kept the leading order expansion, right? If I further expanded, I would have corrections to this that go like 1 plus q over m2 so that will trade an extra power of m2 by a power of q, but now that will be a quantum correction, because it's not something that goes like gmq. It's just something that goes like g times q squared. So this will be something that goes like L Planck squared instead. So instead of Schwarzschild radius, if I just have bare powers of g without any m, this is like 1 over m Planck squared or just L Planck squared. And indeed, this is kind of the leading GR correction to Newton's potential. It's this diagram. So there's something called, okay, so this we'll see tomorrow, but there's something called post-Minkowskian expansion, which is precisely this expansion in gm over r in weak fields. And this is the leading post-Minkowskian correction to Newton's potential. Okay, there's also some function of velocity that comes in, because here I was just counting powers of the masses, but of course the velocities are also caught in. But I just wanted to show that indeed, as promised, this is a correction of the type that we were interested in. Okay, so let me summarize these power counting rules. Actually, let me stop for questions, because I haven't gotten any for a while, and I'm starting to get worried. Yes?
Why in dimensional regularization this zero in the overlap? Because traditionally we can use a dimensional regularization for infrared divergences or UV divergences. Could you explain again this fact, please?
So whenever you have an integral in dimensional regularization,
yeah,
which is scaleless, then this integral is automatically set to 0 by definition. Why is that? Like, one quick way to show this is that you can compute this integral. You can write this integral in terms of some total derivative. So I could just write L dd, like derivative with respect to L of this. So if I wrote then, because this is homogeneous in L,
okay,
this is going to give me an equation that looks like d minus some integer times the same integral again.
okay,
Right? And in dimensional regularization, total derivatives are 0 because there's some dimension low enough or high enough where this derivative is 0.
No, you have a reason. But my confusion is we have an overlap.
Yeah.
Probably it's between soft and hard regime.
Yes.
What is the how to regularize it if I don't have, or it's a infrared divergence, or so far, or I doesn't find, or
Well, I mean, this integral is weird because it has an infrared power divergence,
Yeah.
which is something that is very uncommon. But this is just this example. So generically, the overlap can be like UV divergent, IR divergent. I don't care. Like, I just care that I'm computing this in some scheme.
okay. Okay.
Some regularization scheme, which is dimensional regularization. And this method of regions only works in dimensional regularization. If you were using some other regulator, so first I need to decide with which regulator I'm going to compute the amplitude. Then I can try to study its power expansion in various parameters. So if you use some other regulator, you would have to work very hard because you would have to introduce this arbitrary cutoff in the integration domain,
Yeah.
expanding each region, add them up. But because of this cute fact of dimensional regularization, I can skip all of that and just expand the integrand and do the integral over all values of L.
Okay, thank you.
Yeah. Okay, more questions.
You have a question?
Okay.
No, she's on the line.
Okay. Julio, maybe I'm making some confusion here, but this seems to me a lot similar to calculating the leading singularity of that diagram. Like the arguments are kind of similar.
So for whoever doesn't know what the leading singularity is basically if you compute this integral, putting all propagators on shell. Turns out that at one loop, there is a relationship between, just because this is rational, they're just computing some rational part between this leading singularity of this triangle and the classical contribution. It's an accident of one loop.
Okay.
More generally, it's not true. Yeah.
Okay,
But,
okay.
but if you just care about the rational prefactor of the integral, this integral is purely rational, so the rational prefactor is the answer. But more generally, you need to compute. Yeah. Here, we're not even computing. We're just power counting to understand the dependence on Q or on B. Okay, so let me just summarize these rules of power counting. So the idea is per each vertex with particle I just add 1 power of the mass. Per each propagator of a massive particle, I just add kind of a 1 over Q in the power of the mass. For each graviton propagator, I add 1 over Q squared. Each graviton vertex, Q squared, and the measure okay, and with this simple rule, you can just look at any diagram. Okay, this is at leading order. This one has corrections. But with this simple rule, you can look at any diagram and just look for the classical pieces. Okay? We did it here for the simplest example, which was this triangle, so the leading nonlinearity in G. But now you can look at any diagram and extract the classical pieces. So I think I won't have time to do exponentiation today, but let me do another diagram, which is the bubble, and we'll see that the bubble is actually quantum. As you might expect, because if you have a loop of gravitons, then it better be quantum. A loop then involves matter, as we saw, it's a bit more subtle. But hopefully loops of gravitons are quantum. Okay, so let's very quickly power count this bubble diagram with these rules. Okay, so I have G squared. I have 1, 2, 3, 4. Okay, I have the measure, one loop, which will give me a Q to the D. 1, 2, 3, 4 graviton propagators. So this will be me Q squared to the 4th. 1, 2 graviton vertices. So this goes, and powers of the mass, I have m1 squared, m2 squared. So what does this look like? This looks like G, M1, M2 squared. And this is D plus 4 minus 8. So I have Q to the D minus 4. So this gives me essentially a log Q. So see that this diagram, sorry, yes. This diagram is suppressed with respect to the leading order. So the leading order was G, M1, M2 over Q squared. And this, the suppression is G, Q squared times the log. Okay, so this is not a correction that goes like GMQ. It's a correction that goes like GQ squared. So this is actually quantum. You can even, if you do the Fourier transform of these diagrams, so in the problem set, I asked you to do the Fourier transform of the tree-level diagram, just a 3D Fourier transform to extract the potential. Then you will find that this actually calculates, so it's still non-analytic in Q. It has a log Q here. So this, if I do the 3D Fourier transform, this will give me a correction to Newton that looks like GM1 M2 over R times L Planck squared over R squared. So it's quantum, but it's computable. Okay? So this is also a lesson which there are kind of quantum gravity corrections to things like a potential that we can compute because they're long distance. So they're non-analytic pieces that whose coefficient doesn't depend on any counter term because it's fixed in terms of kind of lower point things. So remember we discussed in the first lecture that whenever you have a logarithm, typically the coefficient of that logarithm is fixed in terms of some simpler amplitude. So this is an example of this. So there's a computable quantum correction to Newton's potential that, that it's a prediction from low energy quantum gravity and is not affected by any short distance singularities. And it would be in a diagram like this. Okay, there was a question, yes.
So can you repeat again what are the M1 and M2 contribution?
Just from these two vertices. So each vertex from this rule here. So each vertex just contributes a power of, yeah. More questions? Yes?
When you exchange a lot of current, can you do that as a classical coherent state?
So when you emit gravitons, you form, at least to leading order, a coherent state. There's a discussion in the literature whether the state in actual gravity, because the theory is nonlinear, is coherent or not. So for instance, last week I wrote a paper, put out a paper with some friends where we give some evidence that actually the state of kind of gravitational wave that we typically measure is not coherent because there's kind of correlations having to do with the kind of nonlinear nature of GR. So it's something called like the nonlinear memory effect, if anyone works on kind of this kind of stuff. But not this exchange. So this exchange, if you want, what they do is they build coherently this phase of the amplitude, but it's not really a coherent state of gravitons, of on-shell gravitons. Yeah. In fact, because this Q is very small, it's these gravitons that are exchanged are very off-shell. That's where we can think of them as some potential. Yeah. Hey, by the way, this was the correction here. If I did the Fourier transform of this here, then I would have just gotten a GM over R correction to Newton. So I would have GM1, M2 over R, and then GM over R. So this would be really a classical correction to the Newton potential. Okay, so what we're going to do next time is to do the hardest diagram. Actually, it won't be hard now because we already know how to power count. But I will do the box diagram. And what we will find is that at leading order in this classical expansion, this won't be suppressed by GMQ, like the triangle relative to the tree level, but in fact, this will go in the classical limit like the square of the tree level. And this is where we start to see this exponentiation. So we'll see precisely how we can see this exponentiation happening, which thanks to this diagram, which then will continue to all the diagrams that look like this, okay? And really kind of let us transition from this Born regime where we just have tree-level diagrams for very low energies into kind of coherent graviton exchange that build up the classical dynamics. Okay, more questions?
You said that the loops are not necessarily only for non-classical effects.
Yeah.
So can you give an example of that?
I just did.
Oh.
The triangle diagram well, this also. I just told you that this is the square of the tree.
Okay.
But we computed the triangle, right? So the triangle, we saw that, okay, so this one will go like GM1, M2 squared over Q squared. And then the coefficient of this will just be GM1, M2. So this won't be suppressed by GMQ. This diagram, we saw that it goes like GM1 squared, M2 squared over Q squared, which is the tree, suppressed by G M2Q. So this is a classical correction. Remember, we had two small parameters, Q over M and GMQ. GMQ encoded just some classical weak field correction. And we also saw this diagram here, which went like the tree, and then the suppression is GQ squared with a log. But that's not important. The important thing is it's not suppressed by GM1 and GM1. Right? So this is classical correction. This is also a classical correction, but this one is just the square of the tree. So this is this information we already have from the tree level. So these two are an example of classical pieces being hidden inside of loops.
So only by power counting can we know when the diagrams are classical?
Yes, yes. So if you follow these rules, you can just figure it out. And the idea is that at the classical diagrams, so at L loops, you just need to find diagrams that go like Q to the L minus 2 in Q. And those will always be, or kind of lower, sorry, or higher. So all of those will be classical corrections. Anything that goes beyond this, so this is classical.
Okay.
Yeah.
But why do you think it is so prevalent, the false statement that only tree-level diagrams are classical? Why? Why do you think so?
So I think that's because in theories where you don't have masses, in most massless theories that we look at where masses are small, then the kind of, one can rescale, like H bar appears in front of the action. And oftentimes when we do perturbation theory, keeping track of powers of the coupling is the same as keeping track of powers of 1 over H bar. So I think the usual perturbation theory coincides with the H bar perturbation theory. But here we have some large quantity, which is the mass, which if you wish goes like 1 over H bar, because I have a very, very large object, okay? So I need to be careful because I need to take that into account, that kind of the de Broglie wavelength over R is a small parameter, or the inverse is a large parameter.
Okay, thank you.
More questions? We have time for a couple more.
On this topic of classical and quantum contribution from loops, is it okay also to assume like massive loops to be classical?
So massive loops, you mean like if I here put a loop of these scalars?
No, not this one, but like to see those, like we have internal massive lines, and whenever we get this situation, we can like, oh, this is a loop with some massive propagator, so we can for sure assume that it will be a classical contribution.
Typically, you see, like, because the large thing is this mass, and there's this inverse powers of the mass coming from these guys, right? So I think it's a good rule, like it's a good rule of thumb that whenever you see matter propagators, you should you should worry that this might be classical.
Yeah, I usually think of this like this, but
Yeah.
you didn't mention this, so maybe I thought like, oh, maybe I'm thinking wrong.
But it's not always true. For instance, an example is the square of this.
Uh-huh.
So the square of this, which will enter at 3 loops, so you could have a diagram that looks like this. That has a bunch of matter propagators, but it's actually quantum. Another example is even this, at 2 loops. So this is one of these tricky overlap terms, because you see, this is like the classical tree contribution. So this has a 1 over h bar, but this is quantum. So this is order h bar. So you have an h bar over h bar here, so you need to be very careful when computing these things to not include this, because this is a classical contribution that has inverse powers of h bar that comes from the exponent.
But this one I can think about cutting those propagators also, right?
Yeah, you
Okay,
can think about cutting them, but you will still get a contribution,
Okay.
but it won't be classical.
Okay.
Yeah. So it's a subtle business to extract these things, but we know how to do it. Yeah.
Okay, thank you.
I have 2 questions. They're connected. First, I suppose there are like infinite classical corrections. Yeah, I suppose. And then, are there any smart way to like resum everything like in a simple manner and not started to do infinite calculations?
Yeah. So it depends where we are in parameter space. So tomorrow I'll start by drawing now the phase diagram for a binary. So the parameters are things like the separation, the velocity, and the relative masses. So for instance, if you have comparable masses, there is a very nice way to resum, which is you forget about all of this. You just put Einstein's equations in a computer, which is what numerical relativity does, and just solve them. Okay? And that works when you have comparable masses. If the ratio between the masses goes up to 10, then you're dead. So numerical GR doesn't work anymore. And for instance, for future space-based detectors like LISA, where we are going to look at kind of supermassive black holes at the center of our galaxy and maybe some smaller object orbiting, okay, the mass ratios that we expect is 10 to the 5. The typical runtime goes like the square of the mass ratio in weeks. So that would be like 10 to the 10 weeks, so something like 200 billion years if you want to compute like 1 extreme mass ratio in spiral on a computer. So you see that there we cannot do something like that. However, we can exploit this small parameter, which would be the inverse of this mass ratio. And there's this other scheme that I'll explain called self-force expansion, which is an expansion in the mass ratio that then enters there. And the leading order is just the probe limit. So hidden inside of these diagrams, there's something as simple as geodesic motion of a particle in the background of the other particle. Okay? And I'll explain precisely which class of diagrams correspond to the geodesic motion and which class of diagrams correspond to the leading correction to the geodesic motion, which is the leading correction in the mass ratio. And there you can use classical equations of motion, like the geodesic equation or just a Schwarzschild metric to resum an infinite set of these diagrams. So essentially there's 2 ways that we can resum analytically. One is by classical equations of motion. The other one is whenever a logarithm appears in perturbation theory, then we have things like renormalization group and stuff like that that can also help resum those logs. But those are the only 2 ways I know, and there's kind of corners of this parameter space where both of these ways become useful. But if you're somewhere in the bulk of this parameter space where you have comparable masses, then, and like strong coupling, or like moderate mass ratio, strong coupling, then we don't really have a great method. So you have to kind of combine various approaches to try to get a prediction.
Thank you.
Okay. Yeah, go on.
Sorry. No, it was not me.
Yeah, just as you can solve easier the equations of GR using these methods, can this be done for other types of equations, like a big sector of differential equations?
Yeah, I mean, whenever you have some perturbative regime and you can solve a differential equation perturbatively, I mean, there should be something like this. At the end of the day, I'm just solving some differential, like secretly I'm solving some differential equation in perturbation theory. But I'm using that behind it, there's this S matrix that has all these nice properties that I described that I can use to kind of figure out the answer without having to actually write out this differential equation, choose some gauge, et cetera, et cetera.
So at the very least, you should need like the equation to come from a Lagrangian for this to be possible?
Yeah.
Okay. Okay, thank you.
So unless we want to keep Pedro running up and down the stairs, I think we can thank Julio. Just before we go to lunch, let me announce that tomorrow in the first coffee break, we'll have a group picture, okay, for the event. There's going to be another one next week, but we want to have all our speakers without photoshopping them in.